our first unit that we will discuss, or our first topic in here, guys, kind of going to be hopefully a review, a lot of it for you, to kind of get us all on the same page and get us thinking again, is measurement and classifying matter, and obviously safety we've already talked about. There will be questions on your regents at the end of the year dealing with lab safety. They should be gimme points. All right, you'll hear me say that a lot throughout the year. You want to make sure you get all of those gimme points. Okay, but matter and measurement is where we're going to be spending the next couple of weeks. So this is kind of a flow chart of dealing with matter. Who can kind of tell me just kind of briefly what is matter? Like if you were to define it, how would you define what matter is? Don't overthink it. Exactly, guys. It's anything that takes up space. That should hopefully be a review coming out of earth science for you. So it's okay. Anything that takes up space. Now, from there, that's kind of everything for the most part. Everything found on Earth, I would say, falls in the category of matter. Doesn't look the same. So we kind of start to break it down. So there's kind of two routes we can go. The one on the left, it cannot be separated by physical means. What do I mean by separating it physically? What does that mean? Yeah, you can kind of pull it apart or kind of break it. It's pretty easy to separate it by a physical means. We'll be doing that a lot this year where you guys will separate stuff. Then it can also be, it can be separated by a physical means versus it can't be. So there's kind of two categories where things will fall into. So we'll start over there on the left-hand side, and this is going to be a big one. These should be easy questions, but as we go throughout the year, we get more in-depth with stuff. People tend to forget these. So we've got pure substances over here on the left. They cannot be separated by a physical means. You probably are thinking in your mind what means you're going to use to separate them. Okay. So this is where we're dealing with pure. Each piece looks the same. All right. Each piece has the exact same composition. Again, if my handwriting is blurry or if it's sloppy, just let me know. Okay? I do get writing fast sometimes, and my handwriting to begin with is not the greatest, so just let me know. So we've got a pure substance, and that can even be broken down from there. It cannot be separated by chemical means, or it can be separated by chemical means only. Now, we're going to talk about the difference between chemical versus physical here in a little bit. Over here on the left, you've got elements. Okay? Elements are the simplest form of matter. You probably know that already. Okay? But it may trip some of you guys up with some of the questions you're asked later on. Who can give me an example of an element? Just shout it out. Oxygen. Hydrogen. That's it? Those are the only two we know? You should know a lot more by Tuesday. Chlorine. All right? Just throwing that plug out there again. Exactly. Now, there's two types, guys, that we're going to talk about. There's a thing called monatomic, and there's one called diatomic. Now, we'll talk more about those later on in the year. What does mon, that prefix mon, mean? One, okay? So it's one element by itself. So that would be something like my personal favorite, sodium, okay? Diatomic, there are 7 elements that exist in what's called the diatomic state. What does di mean? 2. So they exist in a pair in nature. If they weren't in a pair, they would be highly, highly unstable. So we'll talk later on in the year what those are. One example is chlorine. When chlorine is by itself in a chemical formula, not a compound, just a regular equation, it's always going to have that subscript 2. And it's one of 7 that has that. But we'll talk, like I said, more about that later on. All right, particle diagram at the bottom. All right, if it's diatomic, it's going to look something like this. Notice how those dots or those circles, guys, they're the same. All right, my apologies, Bryce. If you need to slide over, you can feel free to. Okay. Notice how they're the same. It's not different colors. You'll see with the particle diagrams that we're going to look at later on. If it's just a single element, it would just be one circle. Okay. Now, I know that that's 2 different examples of elements right there, also showing something else. So if we don't have just an element, okay, but we can separate them by chemical means, what do you think that's called? Not an element, but a, starts with a C? Compound, right? You guys all knew that. Compound. Those can be broken down further. Another name for a compound is a molecule. So we will talk about those all throughout. So you've got two or more elements chemically combined. When they're combined, it's called a bond. Okay? 2 plus elements chemically bonded. 2 or more elements that are chemically bonded to each other. Who can give me an example of a compound? Somebody I haven't heard from. Something you use every day in life. Carbon dioxide, right? You're producing it right now as you speak or as you breathe. What else? Water. Need it to survive. Anything else? Sugar. Glucose, right. Exactly. You guys have seen these things before. Should not be brand new to you, but we will take them to a whole other level that you've never looked at. So our particle diagram is going to look something like this. You've got one element and then like another element to it. That's typically what water looks like. All right, you got oxygen in the middle. You've got 2 hydrogens hanging off of it. Okay, something like that. So just basic diagrams that we're drawing just to kind of drive that home. So, if we go along that left side of matter, they can't be separated by a physical means. So you've got to do something. You've got to put a lot of energy into separating these things out. Okay, whether you just have a single element or you've got a compound there. To break a compound, it takes a lot. So there's this thing called hydrolysis. We'll talk more about it later this year, of water, where you can actually split the hydrogen and the oxygen in water, and you can actually split them into their individual elements. I wish I had the apparatus. I have one. It's just broken. So I can actually do it, but I'll show you guys like a video of that and what you can do with it. Now, on the flip side, you've got matter that can be separated by a physical means. All right, so these would not be pure substances. If something's not a pure substance, what might you call that? What'd you say? Impure. All right, absolutely. Another way we're going to call that is a mixture. All right. So this is where each piece is going to be different. It's not going to be the same. Now, I use a lot of examples with food in my class, so I apologize if I make you hungry. I'm making myself hungry all the time. The way I like to think about it, we're going to have to classify matter. That's going to be part of your homework, is to start practicing that. Think about it. If I were to eat it, if I were to bite into it, would it be the same every time or would it be different? Okay, so that's kind of the idea you want to think about here to talk about the 2 different types of mixtures. So you got the same composition or different composition throughout. Let's start with same. Anybody know what that mixture is called if it's the same throughout? There you go. Homogeneous versus, what's the other one? Heterogeneous. Tomato, tomato. I know I said it weird. All right. So, homogeneous means uniform. It's the same every time. Okay? Where heterogeneous is going to be what? Different. Not uniform. And food are the best examples of this. Who can give me an example of a homogeneous mixture? All right, nobody has ever given me those examples you guys just said, so hats off to you. Mashed potatoes, I'm going to say no, and we'll talk more about it why. Mac and cheese, probably not, and you'll see why in just a second. Think simpler, like homogeneous mixtures tend to be also known as solutions. All right, that's another name for a homogeneous mixture. So if I add that in there, guys, and make it solutions, what's a solution? What's an example of a solution? Salt water. Absolutely. What else? Maybe. Maybe not, depending on how well it's blended there. Juice. I know there's a lot of athletes in here. What are you supposed to drink after you work out? Okay. Yes, you're absolutely right. You want to replenish with those proteins. There's something else I was thinking of. That's usually what you guys are just like on another level, I think, or something. Yeah. Well, you are. You're absolutely right. It is. You want to replenish that, but you know, I guess back in my day, that's I guess the first time I'm going to say that this year. I'll say that a lot. Back in my day with Gatorade, that's what it was. It's like, oh, we didn't even think about chocolate milk. I mean, don't get me wrong. You're going to hear me talk about chocolate milk a lot. I love it. I drink it every morning. Okay, it's delicious. It's good for you. Why not, right? But Gatorade's what I was thinking of, because chocolate milk. Is that always the same every time you drink it? Okay, now if you buy it in the store, it typically is because there's these things called emulsifiers in it that make it have that really nice, rich, chocolatey flavor all the time. But if you make it yourself, and I'll just say it right now, there's certain things you don't go cheap on. It's Hershey's syrup or nothing. I don't want no Nesquik when you make it or the generic. No, it's Hershey's. If you're using something else besides Hershey's, you're doing it wrong. I'm sorry. I'll just quote me on it. I don't care. What? No. Ovaltine? No. Thank you. This isn't a Christmas story. All right. No. All right. You'll get my humor. I promise you'll get it. I'm being sarcastic, but a little bit.
No, it's completely serious.
All right. So.
I literally do this all the time.
Heterogeneous, guys, is different. Examples. Who can give me an example of a heterogeneous mixture? Salad. It's not the same every time. Okay? You might get a crouton. You might get a tomato. You might get, a carrot. Okay?
I don't like tomatoes either.
I like ketchup and like tomato sauce, but I don't like just tomatoes. No. You said a sandwich, Bryce?
Yeah.
Absolutely. Absolutely. So basically, I'm running out of room, so I'm not going to write spaghetti. But yeah, absolutely, spaghetti would be one. I'll just abbreviate. I'll call it spaghetti. Okay, I guess I'm just going to write it all. I actually didn't have space. So, guys, you get the idea. I'm sure I'm not the first science teacher to talk about heterogeneous versus homogeneous in here. The big thing in this class, though, that might be new is this term, solution. We have a whole unit dedicated to solutions later on in the year, right? We'll talk about that. One of your questions on your lab sheet was dealing with parts per million. That's a concentration which is dealing with solutions, okay? Just remember that's a homogeneous mixture. It can be separated, and we'll talk about separation means on Monday. So, particle diagrams for homogeneous mixture. It's going to be something that's the same throughout. So, it's going to be two different pieces. Or multiple pieces. So these are just like different compounds, but it's the same all throughout. Okay? Where it's the same ratio is what you want to think of. So I've got 1 to 1 to 1 to 1. It's going to be the same every time. So when you drink Gatorade, it should be the same every time. You don't get water in one gulp and powder in the other. It's the same every single time. Kool-Aid, another example. You don't get sugar and then flavoring and then water. It tastes the same. On the flip side, though, heterogeneous, you might have more of one thing, and it's going to be different every single time that you go to eat something out of it. Okay?
I can't tell the difference between.
Yeah, I realize that. So I'm going to go back and erase this. Let's simplify our homogeneous mixture. First lesson of the year. Pencil, pencil, pencil in here. All the time. So I'm going to add a water line, guys, to this just to kind of make you think, hey, it's the same throughout. It's been dissolved, okay? Heterogeneous or homogeneous mixtures typically are dissolved. A lot of liquid type state where you've got one thing dissolved into water, okay? Where heterogeneous mixtures, they look similar at the particle level, all right? But you know the difference, okay? Don't overthink it. That's what I'm getting at here. Don't overthink it. The pictures, I'm trying to do the best I can. I can only show so much with 2D, so don't overthink it.
So they'll be like different colors.
Right.
Okay.
It's gonna be obvious, okay? It'll be obvious to you. And there's another way that as we go along, there's another symbol that you're gonna see in a chemical formula that's gonna automatically tell you it's a solution, okay? Are we good here? Can I go on to the next slide? All right. So here we go. Which particle diagram or diagrams represent a mixture? Now, this can be heterogeneous or homogeneous. Mixture means what? Mixing things. So elaborate more on that.
But it's not a solution.
Okay, it could be, but it doesn't have to be just a solution. Go back to a more basic definition, guys. Look on your flow chart.
Oh, it's
Can be
different.
separated.
Can be separated. But what does it have to have even before you can separate it? Look right here. All right.
It can be pulled apart.
You know what? We got to go back and add something in here. Mixture. It's got 2 plus substances that mix together. I knew there was something I was forgetting when I looked at that. It's got 2 or more substances. So a compound has 2 or more substances, but they're chemically bonded. So notice how with our particle diagram, they were attached to each other, right? Compound, they're going to be attached. Mixtures, 2 or more different substances, but were they attached? No, remember this is our diatomic element right here. It's one element, but these are all just a mixture of different elements. They're not combined together chemically. So when we look at this picture right here, mixture, where do you see different substances physically mixed together, not attached to each other?
2.
Exactly. Number 2 is going to be the only one. Number 1, guys, you've got a compound. Okay, 2, they're chemically bonded. This is how we draw it because the circles are touching. 3 is just a single element. 4 is also a single element. All right, so I'm going to add those in there. This is compound, this is element, and this is an element. What's unique about number 4? Is it a... Oh, that's going to happen from time to time. 3. Pure substances are elements. Is that it? 1. Remember, if you have a compound or an element, guys, when they're just by themselves, it's one thing. 2 is a mixture. You've got 2 different elements. They're not chemically bonded. Number 1, your compound is bonded to each other, so it's just one. That's like water. You have a cup of water, you've got all these H2O molecules that are in the same proximity. Okay? It's a compound, but there's multiple molecules around each other. That's what number 1 is showing you. Which of the following, number 3, represents a mixture of one compound and one element? Compound and an element.
2.
Number 2. Okay, number 2. Number 1 is a mixture of what? How many? 2. You got a couple different compounds in there. Forgot your guys is in black and white. I do apologize for that. Number 3, you've got just an element. I'm sorry, no, you got a compound of 2 different diatomic elements. That's what we're getting at there. Number 4, what particle diagram represents a diatomic? 2 is a single diatomic. 1 is a mixture, or I'm sorry, 1 is a compound. 3 is a mixture of 2 diatomic elements. We're going to do a lot of practice with this, guys, so don't freak out. It's the first time maybe you've seen some of this. It's okay. Like I said, it will be obvious. I'm not trying to get you with it. Let's continue on. Properties of matter. Again, this is hopefully a review. So I'm kind of moving quickly through this. My hope is that it's not brand new to you. Notice a lot of the terms that we're discussing in class, they're vocab terms, so I'm kind of defining them for you. All right, keep that in mind for your vocab. Physical properties. Any idea what a physical property might be? Or what's unique about a physical property?
Something you can see or feel.
Pretty much, all right? Pretty much. So they're kind of constants is the way you want to think about it. About a substance. All right? Senses. Use your senses. You don't need to use chemical analysis to observe them or measure them. What's one example you could give me? Take your time. Finish writing it down. Think about it. What's an example of a physical property? What's that? Texture. What else? Color. Smell. Are we tasting anything though? No, but right, you could taste it. Think a little bit more deeper than just that, like those. There's other ones, guys, like melting point. MP for melting point. Boiling point. Freezing point. Condensation point. All those ones are also physical properties. Now, you have to do a little bit more analysis, but it's still not looking at the chemical structure of them. That's what chemical analysis means, is chemical structure. Okay? Melting point, you leave a piece of chocolate out, you can identify what the melting point is pretty easily. All right? By observing it. You see what happens to it. All right? Now, within physical properties, you have extensive and intensive. Extensive. Any idea? Have you heard that term before? Extensive versus intensive? No? Any idea? Either of them. Extensive versus intensive. What does intensive sound like?
Inside.
Yeah, it's like inside, okay? It does not depend on how much material you have. What would be something that doesn't matter on how much you have? Hint, I've already given you a couple.
I mean, when you're talking about chocolate, if you have a tiny amount of chocolate and like a lot of chocolate, it's still chocolate.
Right, that's the kind of the idea. It's still going to be the same, but a property related to that chocolate. Again, hint, I've already given you a couple. Yeah, melting point. Doesn't matter how much you have, okay? The melting point's not going to change. Like you were saying, Sarah Sue, that the chocolate, if you have a small piece versus a large chocolate bar, it's still going to melt at the same spot because it's the same type of chocolate. Freezing point goes along with that, or boiling point as well. If I abbreviate anything and you guys don't understand what I'm abbreviating, just raise your hand. I'll explain it. Color doesn't matter on the amount you have. Density. Right? That's a ratio of mass to volume. So whether you have a giant block of gold versus a little nugget of gold, it's still gold. The density is still going to be the same. Solubility. That might be a new term to many of you. Anybody know what solubility means? The ability to be dissolved. Yep, to dissolve, right? So it's soluble. So those are some examples. So if intensive doesn't depend on how much you have, extensive is going to what? Exactly. It's going to depend on the amount of substance you have. Examples. What? Yeah. Mass. We'll talk about mass versus weight. What else? Kind of go volume right there with density, right? Those two extensive properties go into giving you density that's actually intensive. A couple others. Energy and heat. Those two are closely related to each other. We're going to find out. All right. Again, my hope is that this is nothing completely brand new. Maybe a little bit of new terminology here or there, but should be hopefully mostly common sense. All right, now chemical properties. So physical, they're constants about a substance. We use our senses. We don't really have to undergo anything. So chemical properties are where you're actually doing a reaction. All right, they are the behaviors. I'm going to change up my colors here just to make it a little easier to see. So they are behaviors of substances. When they react. With other substances. Okay? You're going to see kind of a common theme when we list some examples of chemical properties. Any idea? Burning, right? So we call burning, it's burning, but it's flammability. they just sound more technical. So flammability, which is burning. You've got, oxidation, which is rusting. What'd you say? Somebody else said something else.
Corrosiveness.
What's that?
Corrosiveness.
Yeah, corrosiveness. Okay. They just, again, sound a whole lot more technical than the physical stuff. All right? So just kind of keep it on. We're going to get a lot of practice with this all throughout the year. It's something we're going to continually do because I saw a few questions on it last year's exam. So we want to keep moving along with it. Again, those hopefully should be, they should be gimme points. Good? Can I go on? All right. Let's just do a couple practice problems, and then that'll be it for today. ID the following as intensive, extensive, or chemical. So the first thing you got to ask yourselves, is it talking about the substance's behavior when it reacts with something else, or is it talking about something you can observe? Mass of copper wires, 255 grams. What's that going to be? All right, it's going to be physical, and that's going to be which one you said? Extensive. So remember, these two right here are physical, and then you have chemical by itself. So that's an extensive property. Boiling point of ethyl alcohol is 77 degrees. So it's chemical or physical first. Physical. Now, is it extensive or intensive? It's going to change based on the amount. Yeah, intensive. It's not going to change based on the amount. Baking soda reacts. Right there, that tells you what? Chemical. Density of mercury is intensive. And then solubility of sodium chloride in water, intensive. All right?